Is audio better?
Yes, sir.
Okay. So shall we directly jump into the problems and solve the fear? So keep your calculators ready, papers and pens ready. Okay. And this is the problem given here. A wall of a furnace is made up of inside layer of silica brick of 120 thick, covered with a layer of what is this magnesite brick, which is of 240 thick. So there are two blocks of walls here. That means if they think this is a furnace like this, okay, this particular furnace is being built up with two different layers. Okay, that is what he is saying. Okay, the first layer is just better draw with some. Okay, so he says there are two segments of the wall. Okay, like this. Okay, now this is your core of the furnace. So whatever it is there inside, so this is your core, the furnace core, and it is covered with two walls. He says that means the wall number one is this one, this particular wall here. So this is your wall number one, and another wall he says which is this. Okay, so this is the overall picture. Okay, so this is how the furnace is built up now. So the wall of the furnace is made up of inside layer of silica brick. That means this particular thing here is of silica brick inside. Okay, that means I can draw a parallel diagram like this, right? So this is one wall here, like this, another wall. Two walls are there. The first wall is made up of silica brick. Okay, this is just an extension. If you could imagine the things. So this is just an extension of this like this. Okay, nav. So what else he says? Silica brick is 120 thick. That means this particular thing here is 120 It is 120 thick. Next, what he says, with the layer of magnesite brick of 240 so another layer is of magnesite, which is this. So there's anything you can say, which is the magnesite, and this particular thickness is being 240 as given there. Okay, so this is the 240 thick. The temperature at the inside surface of a silica brick wall and outside surface of a magnesite brick wall is 725 and 110 degrees Celsius respectively. So which temperatures as these? So I can draw three temperature curves here or spots here. So this could be T1 and this could be T2 and this could be T3. Okay. Now, so in the given problem here, the temperature at the inside surface of a silica brick wall and outside surface of a magnesite brick wall are 725 and 110 degrees Celsius, he says. So 725 and 110 degrees Celsius. What are these temperatures and what I'm supposed to take these as? Which one is T1? Which one is T2? Which one is T3? The given temperatures of 725 and 110 as indicated by the problem here. Which temperature should I take 725 as or 110 as? Yes. Amrit.
Yes. Yes.
Okay. So, which temperature are this given? So, he has said something about 725. He has said something about 110. What are these? What I'm supposed to take it as? Should I take it as T1 as 725? Should I take it as T2 as 725? What is that?
725 Steven.
725 is T1. So, how did you come to this particular conclusion here? Yes, Amrit. How did you come to this conclusion?
So, initially, to transfer heat, it has to be more. So I thought,
Your answer is somewhat right, but how did you come to that conclusion? Prajat Rai.
Yes, sir. Sir,
So, how did you come to this conclusion?
it's given, right, sir, in the question. The temperature at the inside surface
Where?
of the brick and outside surface of the brick are 725,
Magnesite
magnesite
and
725,
110
and
respectively.
this,
110. So, you say
the
that
first one goes for the
first one goes for the inside surface of the silica brick. So, this is your silica brick, right? Which is this. The inside surface is being this one, which is this one, right? Correct? So that particular temperature is what? T1. So T1 is just 725. That is how we have to judge the things. And the other one is outside surface of the magnesite brick wall. So magnesite brick wall is this one. Magnesite brick wall is this one. Outside surface in the sense this is our outside surface. So if it goes for the outside, then it should be T3. That is the value of T3 is 110. All of you got this? Any doubts, if at all, if you have? Yes, any doubts here?
No, sir.
Okay, so
not yet.
T1 is clearly given it as 725 degrees Celsius, whereas the value of T3 he has given it as 110 degrees Celsius. Next, the contact thermal resistance between the two walls at the interface is 0.0035 degrees Celsius per watt. Okay, so he has given the contact resistance. If he has given the contact resistance, what happens? So I'll give you two illustrations now. Number one is I am drawing the temperature drop curve here. So initially it will be at, please everyone engage here. Initially it would be at T1, it drops to T2 and at this level, and further it drops to T3. So this is one case. Okay, this is one case. In another case, what I will be doing, I'll just try to draw the same thing here. Okay, now we'll just draw it. Now, from the temperature T1, it drops up to T2 here. Next, again, because of the contact resistance, it drops T3 at this block. And further, it drops to T4 here. At this bottom, he has given the contact resistance here. So, which case am I supposed to take? Whether should I take it a case 1 or should I consider it to be a case 2 because of the presence of contact resistance there? Yes. What should I consider it as? Should I consider it as the case 1 or should I take it as case 2? While the contact thermal resistance being given between the walls. Yes, man, Benoit. Benoit.
Not sure.
So, which case am I supposed to take? Should I consider it to be a case 1? Should I consider it to be a case 2? While the contact thermal resistance is given.
I think it's case one.
You think it's case 1, so just mark one port for this. Okay, what about remaining? Karthik,
Case 2, sir.
case 2. So Karthik says it's case 2. What about remaining?
Case 1, sir.
Case two.
Thermal contact resistance is given as something 0.7. Yes, given. Okay, now. Someone said I could not able to concentrate. Sorry, can you could repeat it? Yes, case 1 or case 2. Out of 31, I have received only 2 votes right now. I need all 30.
Case two.
Case 2 or me. Okay.
Case 2.
Amrit, case 1 or 2?
Case 2.
Remaining all the people, man. Adarsh P, Amrit, Ashwin, where are you? Should I consider it to be a case 1 or should I consider it to be a case 2? Adarsh, case 2 again. Suraj also case 2. All the remaining guys were Nafa, Namita, Numan, Nitin, Rakshan, Reza. Where are you all? Shravan,
Yes, sir.
Shahzad, okay.
Yeah.
So most of you are going with case 2. So by this, I came to know that all of you, in fact, 50% of you are just online but not physically present there, right? If you guys don't involve, it's no meaning in taking a repetitive class on the same problems, man, whatever we have dealt, right? You have to involve. So if it is making you burden, I will just short it for 20 minutes or 30 minutes. But the thing is, you have to involve in whatever time you are spending and make it a valuable time spent, right? See, no one are answering only how many? 5 plus 3, 8, and 9. What about remaining? 30 people are there, 30 people. The class strength is 60. Out of that, 30 people are present. Out of 30, only 11 have answered. I will not move on unless this number reaches here, man. Sujay Shetty, Shravan, Sagar, Namita, Tausif Ali, Faizan, Chandan. Case 1. 22 people. Still 8 need to give the answer. Okay, fine. So, those who have said case 1, why do you think it has case 1? Any reason? Why do you think it has case 1? Those who have said case 1. For example, Prajatrai. Prajatrai, are you there?
Yes, sir.
So, why do you think it has case 1? Why not case 2?
So I don't know, sir, because the previous sum which you gave, sir, it referred to case one, so that's why I said question.
Okay, fine, fine. Tausif Ali. Muhammad Tausif Ali. Not there. Okay, so listen here. From the next class, what we'll be doing is at the initial start itself, we will mark the attendance within, suppose, in case of today, the class started at how much? 10:15, right? So within 10:20, we will finish up the attendance. Okay, so attendance part will be done there. And during an interactive session, whoever is not responding, directly they will be marked absent. Okay, so this procedure or this methodology we shall follow from the next class. So remember, after 10:20, they will not be marked present once again. Okay, so you'll come to know the strength of the class within 10:15 to 10:20. That means the first initial 5 minutes of the class, you must be present and give your attendance. Okay, if at all you were called in between the class and you are in a position that you did not answer it, then you lose your attendance for that class. This is the procedure will be followed from the next class. Okay, remember. Just a second. So, Shravan, whoever said case 2, not only Shravan, most of you have gone with case 2. Why case 2 is my question. Why case 2?
Temperature T2 and T3 is between the walls, sir.
Okay.
So I think that is the reason.
Okay. That's okay, but not a proper reason. Why case 2? Raise a.
So because T2 is equals to T3.
If T2 is equals to T3, then it should be case 1, right? Then
So no case 2, no.
okay. Don't get confused with the x-axis. See, temperature is being measured in this way. So T1 indicates it is at higher pressure, higher temperature. T2 is a little bit lower, and T3 is lower than that of T2. Okay. So it's been measured in the y-axis like this. Yes. Any other answers? Why case 2?
There is a resistance in that wall, sir.
Exactly. That is what has to be highlighted in this particular problem. So in this problem, What he has given us the contact resistance. That means, what is the contact resistance? At the contact, okay, suppose if the temperature is dropping like this, at the contact, because of the presence of air, this temperature drop will suddenly drop at the contact surface. This amount of temperature drop is accounted for the contact resistance which is there between the between the two surfaces. So contact surface offers some sort of resistance to the temperature flow, where there is, you can observe a steep drop in the temperature. This is just because of your contact resistance. So since he has given the contact resistance in the problem, you are supposed to take the case 2. So why you have to take the case 2? Why? Because the contact resistance at the contact is being given. Clear?
Yes, sir.
Everyone?
Yes, sir.
Okay, this is very, very important when you know to understand this. Okay, so I'll just rub all this and draw a absolute clean figure. So what's happening here? So initially there is a silica wall brick and there is a magnesite brick. So this I can name it as silica and this I can name it as magnesite wall brick. Okay, the temperature drop because of the presence of the contact resistance. So I can take this particular temperature T1 to be how much? 7 something he has given, right? 725 degrees centigrade. And this I can take it as T2 and this I can take it as T3, whereas T4 is this particular point, which is 110, I guess. So it's 100. So this is the temperature profile now. I think he has even mentioned or given us the length of these two. Yes. So how much is the length? 120 and 240 mm thick. So I will just consider this to be the block A and this to be the block B, so that I can name this as LA is equals to 120 mm and LB is equals to 240 mm. Great. So these are all the things factored until now. Per unit wall area. Next. If the thermal conductivities of silica magnetous brick is 1.7 and 5.8, so what he has given us the value of Ka. How much is the value of Ka? 1.7 watt per meter degree Celsius. Even he has given the thermal conductivity value of B, which is magnesite, as 5.8 watt per meter degree Celsius. Calculate. So these are the things he has given. Now, what we are supposed to find? To find the rate of heat loss per unit area of the wall. So rate of heat loss in the sense you need to find the value of Q here. And the temperature drop at the interface, that means what is T2 minus T3. So this gives or this accounts for the temperature drop. This we have to find. Okay. So these two questions are being asked in this particular problem here. Okay. Ready? Shall we solve? Are your calculators ready? Everyone, man.
Yes, sir.
Shall we start solving it?
Yes, sir.
Keep your calculators ready. Okay. So same thing. First, you have to find what is the amount of heat which is flowing common, that is heat flux which is flowing common throughout the surface, and that is given by Q is equals to temperature difference divided by the total resistance. Okay. So this particular total resistance or total resistance is summation of three resistances here. So this particular resistance is summation of three resistance. What are those? The number one is the thermal resistance which is offered by the block A plus the contact resistance plus the thermal resistance which is offered by block B. Am I correct? Or any other resistance I still need to add it. So the first, because of the thermal resistance which is offered by block A, the temperature drops from T1 to T2. Because of the contact resistance between the block A and B, the temperature drops from T2 to T3. Similarly, because of the thermal resistance offered by block B, the temperature drops from T3 to T4. Any other any other resistance should I add to the summation of the resistance from T1 to T4? So all the resistance are being covered, right? Taken care of.
Yes, sir.
Okay, great. So now, in this case, we shall just try to elaborate this. This is equals to, how should I calculate the thermal resistance offered by block A, which is conductive resistance? It is given by L divided by Ka, right?
Yes, sir.
Hope you remember this. So this is for the block A plus resistance, contact thermal resistance. I think he has given the problem. How much is it? 0.0035 degrees Celsius per watt. So you can just directly substitute that value, that is 0.0035. See, degrees Celsius per watt he has given. So that is the thing. Plus LB, L by Ka of the block B. This is for the block B. Okay. Now, since the area is common throughout the surface, or if I want to calculate, just a minute. If I just want to calculate the heat flux, I can neglect the area because it is the watt per meter square. So meter square in the sense area can be eliminated. So it would be LA divided by Ka plus it by Kb. I think you know all the values. Just substitute those and give me the answer. See, remember to substitute in meters is 0.12, correct? 120 mm in terms of meters. Can I take it as 0.12? Am I right?
Yes.
So K is again 1.7 plus 0.0035 plus LB is 0.24, substituting in meters. Be careful about it. And KB is 5.8. Now, give me the total resistance, summation of total resistance, thermal resistance. So this should be degrees Celsius per watt.
0.314, sir.
Okay, 0.314.
No, sir. No, sir.
Just check the values. If you got the same
Sir,
value,
I got 0.1154.
okay, fine. How much?
1154.
1154. Just check the value. If you got the same value, you can raise your hands, or else you can switch on your mic and say that is wrong. Good. Very good. So, accepting this as an answer, we shall move further. So, next, we shall calculate what is the value of Kiev. So, Kiev is equals to, you can take this equation 1. So, Kiev is equals to delta T. So, delta T in the sense, which temperature difference should I take? I should take T1 minus T4. So T1 minus T4 divided by sigma resistance thermal. So that is equal to T1 is 725 minus T4 is 110 divided by your resistance cumulative is 0.1154. Now, what is the value of total heat flux which is going through the material now? This should be in watt per meter square. Yes, what's the value? Okay,
5,329.
5,329. Okay, I think everyone has got the same value. Fine. So next, our main target is we have found out what is KIF. Correct? So KIF we have found it as it is 5329 something. So this is done. Next, I have to find what is the value of T2 and T3. So any idea so that I can find what is the value of T2 and what is the value of T3? Since I found out Q. So I have the value of Q which is flowing throughout the wall. So how can I calculate the value of T2 or T3? So first we shall discuss about this block. I have to calculate the value of T2. I know the value of Q which is flowing. Any idea?
So we can use this Q is equal to T2 minus T3 divided by R contact.
Okay, come again.
Q is equal to T2 minus T3 divided by R contact.
Or contact. Huh? Okay. Let me clear this now. Whether this R contact, the resistance R contact, what do you mean by R contact? First of all, let me clarify this.
Resistance offered by the contact
Correction.
surface.
Okay, resistance offered by the contact. Okay, it's fine. If the resistance offered by the contact is responsible, listen my question. The resistance offered by the contact, whether it is responsible to decrease temperature from T2 to T3 or to decrease it from T1 to T2. The contact resistance, whichever is offering, whether it is responsible to decrease from the temperature from T2 to T3 or because of the contact resistance, the temperature drops from T1 to T2. Just think.
So T2 to T3.
Right? So it's better I put that Q is equals to T2 minus of T3 divided by our contact. So which one is correct option according to you? The number 1 or number 2?
Sir, I told second one, sir.
Okay, you told the second one. Then great. I'll just drop this off. So for the second one, how will you calculate using this? Okay, let us evaluate this one. So you know the value of Kev, great. You know the value of contact resistance, great. You don't know the value of T2. You don't know the value of T3. Two unknowns and a single equation, impossible to calculate, right? Yes, Shahzad.
Yes, sir.
So how to proceed with this? I want the values of T2 and T3 to be calculated.
We can use this one. Same, sir. Q is equal to T1 minus T2 divided by R E.
Once again. Okay, yes, Rakshan. What I'm supposed to do now? You said something.
Yes, sir. This one, Q is equal to T1 minus T2 divided by R A, resistance offered by the block E.
That's great. So resistance, if you consider the resistance offered by the block A, then we shall see, then we'll evaluate the things now. You know the value of K, you know the resistance offered by A, yes or no? Because L by K is known and T1 is known, you can calculate the value of T2. Excellent traction. So that is what you have to do. You have to apply the Fourier law for the block 1. That means the electrical analogy or whatever you say, all the thermal concepts remain same. Just apply this for the block 1. Okay, so applying that for the block 1, what you'll have. So Kev is equals to for block A. So Kev is equals to T1 minus of T2 divided by the thermal resistance which is offered by the block A. So Kev we have just calculated it to be 5329 is equals to T1. How much it was, 725 something, minus T2 is supposed to calculate, and resistance offered by A, resistance, conductor resistance offered by L by K, that is LA by KA, right? So if we go for the substitute, 589 is equals to 725 minus of T2 divided by, what is the LA is set as 0.12 divided by K 0.7. Solve it and give me the value of T2. Yes, what's the answer?
$340.
348. So if you got the same value, you can just raise your hands.
Yes, sir.
Great. Sagar. Right. Now, so this is the way you have calculated. Good. So this is the way you have calculated the value of T2. So now you have got the value of T2 now. So how to proceed with T3? So how to proceed with T3? Now I am supposed to calculate the value of T3. So how to do it?
So we can do it either T2 minus T3 or T3 minus T4.
Excellent, Saga. You can go with Q is equals to considering T2 minus T3 where it is because of thermal contact resistance, or you can go with Q is equals to T3 minus T4. This is because of the thermal resistance or conductive resistance which is offered by block P. Either of the way you can do it. So anyone you can follow, this or this, and give me the value of T3. So finally, we are supposed to calculate the temperature drop, which is nothing but T2 minus T3. Even you give me this value also. So there ends your problem. Yes, what's the value?
Sir, 330.2.
Okay. Which one is that? T3?
T3, sir.
330. Okay. I can just take it as 330. Then delta T, the temperature drop. Just subtract these two. It's around 17 or 18.
18.
18.
Okay. Or if you got the value, just raise your hands. If it is a different value, then let me know. Good, Suraj. Good, Panay. Nathan. Shahzad, Amita, Subat, Grace, and others. Good, guys. So that was the problem. Okay. So most of you have got it. Any doubts in this particular problem? So this introduced us to our concept of the contact resistance. Okay. Any doubts in this particular problem?
No, sir.
Just hang on for a second and start attendance online.